Okay, this problem is going to be a proof as it asks for. So it reads, the equation 1 over dO plus 1 over di equals 1 over f is called the Gaussian form of the thin lens equation. The drawing shows the variables dO, di, and f. The drawing also shows the distances x and x prime, which are respectively the distance from the object to the focal point on the left of the lens and the distance from the focal point on the right of the lens to the image. An equivalent form of the thin lens equation involving x, x prime, and f is called the Newtonian form. Show that the Newtonian form of the thin lens equation can be written as x times x prime equals f squared. So a whole bunch of algebra. So we have to come up with, after this algebra here, with that x, this distance down here, times x prime, this distance down here, equals f squared. And we have to start out with the thin lens equation that we're used to, so 1 over dO plus 1 over di equals 1 over f. So this is the ultimate goal, but we have to start with this one. Okay, so for one thing, the Newtonian form doesn't have any inverses in it, so what I could do is multiply everything in here with, let me move this over a little bit, gain some space, multiply everything in here with dO, di, and f, and I would come up with di, let's see, di times f plus dO times f equals dO times di. Well, it seems like I haven't gained much. Well, I did actually. I got rid of the denominators and I only have one straight equation here. What I'm going to do now, though, is that in order to come up with these x and x primes, I have to get rid of the di and dO, and that is being done is that di is equals f plus x prime and something similar for dO, and that's what I'm going to substitute. This one is going to be a really long one, so I'm going to start here on the left. So di is the same as f plus x prime, and I think what I'm actually going to do is I'm just going to type it because I don't have any more. I don't have any more fractions here. I think I'm just going to type it. So I'm going to have di equals f plus x prime times the f plus the dO is f plus x times f, and then that equals the dO again is this one here times di. There you go. Okay. And now I factor out. Actually, I'm not sure if this is going to be too small here, so there we'll make it bigger. And then I'm kind of in my own way here. I don't need this actually. Alright, so I'm going to factor this all out, so I'm going to come up with f squared plus x prime f plus f squared plus x times f, and that equals, on the right hand side I have to FOIL, so it's going to be f squared plus fx prime plus x f plus x times x prime. Okay, and again make this a little bigger, and then I'm gonna look at it and hopefully am able to take my red marker and say that, okay, I got an f squared here and an f squared here. That would make 2f squared, but I got another one on the other side. So which means that one on the other side here actually cancels. One on the left hand side is subtracted, come out with 0 here. Then I'm going to see that there's fx prime right here. Hold on. I like to cross it out in the other direction so you can see that this one takes care of this. And then there is an xf right here, which is over here as well, xf. And you can see that, I'll type it out again, that f squared equals x times x prime. Indeed. Done. This problem reads, a converging lens with focal length of 12.0 centimeters is located 30.0 centimeters to the left of a diverging lens of focal length negative 6.00 centimeters. A postage stamp is placed 36 centimeters to the left of the converging lens. Locate the final image of the stamp relative to the diverging lens. Find the overall magnification. Is the final image real or virtual with respect to the original object? Is the final image upright or inverted? And is it larger or smaller? Analyzing this whole thing with a ray diagram would be quite a bit of work that is going to be more or less accurate. So instead I'm just going to use the thin lens equation and we'll apply it twice. Okay, here is the converging lens, and each of these here should represent, let's see, converging lens 12 centimeters. Okay, so each of these boxes here should represent 10 centimeters, so we have a focal length of 12 centimeters. There it is again, 12 centimeters, and they're 30 centimeters apart, and here we have 6 centimeters and another 6 centimeters, and then the image is over here. This lighthouse is at 36 centimeters from the lens. Let me make this just slightly smaller. There we go, 36 centimeters. Okay, so I'm going to apply the thin lens equation. I didn't mean to have this in red, but oh well. With this one here being the 6 centimeters, I'm sorry, the 12 centimeters for the convex lens, and then this one here being 36 centimeters for the object distance. And then, oh, I just noticed that actually my lighthouse is possibly off the screen. Sorry. And when I do that, I'm going to come up with an image distance of, let's see, 1 over 12 plus, oops, minus 1 over 36, invert, come up with 18 centimeters, and that would be to the right of the lens, and I have to invert that. There we go, and 18 centimeters is going to be approximately here, and because it's a whole lot closer, it will appear smaller. In fact, it's half the distance, so it would appear half as large as the other as the original one. Okay, now the concave lens is going to see this image over here, and it has a distance here of, let's see, this is 18 centimeters here, so that makes this one here 12 centimeters. So its DO is 12 centimeters. So this DI here is subtracted from the 30 centimeters total here that the lenses are apart, and I come up with a new object distance for the concave lens of 12 centimeters. So this one is the concave one, and then again it's going to be the thin lens equation, 1 over F equals 1 over DO plus 1 over DI. So this one here is, as I just said, 12.0 centimeters, and the focal length of the concave lens is given in the book as negative 6.00 centimeters. Of course, it makes sense that it should be negative because it's a concave lens. And again, plugging that in. Is going to be, let's see, this is a negative 6 minus 1 over 12, and invert that, and I come up with negative 4. So I end up with this one here being yet another size 3 times smaller, and it should be sitting about there. That should be the final image. The DI came out to negative 4 centimeters, and then of course a concave lens is producing a virtual image anyway. As far as looking at a postage stamp in that way, that was not very convenient. It just makes the whole postage stamp a whole lot smaller, this kind of assembly, but I guess that's the physics problem here. So let's see, what did they actually want to know? Locate the final image of the stamp relative to the diverging lens. So there it is, DI equals negative 4 centimeters. Then find the overall magnification. So the magnification earlier was, let's see, M equals negative DI over DO, and that was negative 18 over 36, so that was a minus 1/2. The minus meaning it's inverted, and that's why we saw this about half as small as the original one. And then with the concave lens, it's going to be M equals its negative its image distance over its object distance. So that was that negative 4 over 12. So negative negative is a positive, so that comes up with a positive 1/3. The positive meaning here that the image was not turned around anymore after that. And then put these two together. Whoops, running out of space, of course. Multiply these two here, come up with an overall magnification of negative 1/6, and that means that the original image over here was turned upside down and comes up with 1/6 of its original size. And the rest of the questions I had already answered. Is the final image real or virtual? It is virtual. It's being produced by a concave lens. With respect to the original Object is the final image, upright or inverted. It is inverted. And is it larger or smaller? It is smaller. So and here's with an applet. Okay, put a lens in there. The lens should have a focal length of 12 centimeters, and notice the number down here is again off by a factor of 10. Oh well. So the 1.2 here means 12 centimeters. Is that what it was? Yeah. And the lens itself should be situated at 36 centimeters, and you can see that here, and when I put the pointer here you can also see it on the lower left. Then I'm going to put a concave lens in there, and what I do is I push the focal point to the other side, and there it is. Notice that I had to use a different applet here, so my focal length should be negative 0.6. Where'd it go? There, right there. Okay, and then the lens should be 30 centimeters away, so 6.6 right there. Okay, and actually, yeah, and I'm going to put an object in here. Let's see what kind of object they give me. They give me a stupid arrow. Oh well, I try to push it as far as I can here. I only get to 0.01. Let's see, it has a height of, actually let me make the height to be divisible by 6. So how about 0.9? Right, come on, right there. Alright, 0.91 is the height of the object. That's okay. Here is the image, and the image has a height, the final image that is, it has a height of negative 0.16. I guess that's rounded from 0.91 divided by 6. And it has an image distance of, let's see, a total distance of 6.2, and the concave lens has 6.6, so yeah, that is indeed negative 0.4, respectively negative 4 when multiplied by 10 to adjust the different units in this applet. In this problem, it says a far-sighted person has a near point that is 67.0 centimeters from her eyes. She wears eyeglasses that are designed to enable her to read a newspaper held at a distance of 25.0 centimeters from her eyes. Find the focal length of the eyeglasses, assuming that they are worn 2.2 centimeters from the eyes and 3.3 centimeters from the eyes. So here you can see is here's 0, here's would be 60, and then here's 67. That would be her near point. That means she can see everything beyond this, but in between that near point and her eye, things become blurry. So she would have to hold a newspaper over here 67 centimeters away. That's about 2 feet away in order to still be able to read it. So she's going to grab reading glasses. Reading glasses are convex. If you can see, if you look closely, then I chose glasses here that are more convex than they are concave, making for an overall meniscus convex lens, and those would be reading glasses. They should be placed about 2 centimeters from the eye, so really close here, kind of like around there. Okay, and that would then pull the near point to, as it says, 25 centimeters if these eyeglasses have the correct focal length, and that would then, now she can read the newspaper just holding it about 10 inches away. And they're saying to use the thin lens equation. So 1 over f equals 1 over do minus 1 over di, and we're looking for f. So the object should be held at 25 centimeters from the eye, respectively. From the lens, it would be 25 centimeters minus the 2.2 centimeters, because that's how far out the lens is. And then the image should appear at 67 centimeters, because that's where the original near point is for the person. And this one is going to be the image, therefore it's going to be on the same side here on the left hand side, so that image distance is going to be negative. So I'm going to write this down here, and then I notice I made a mistake earlier. I'll point it out in a moment. So this one is this one here. So that's going to be a negative 67.0 centimeters, but it's 2.2 centimeters closer, and I would have to put this one here in parentheses, because this total distance here is from that original near point to the lens itself, and that of course is 2.2 centimeters shorter, but it's considered a negative because the image is on the same side, on the same left side as the object is. Okay, here's my mistake. Sorry about this. That of course is a positive right there. Okay, plugging in numbers means that the focal length is going to come out to it's going to be kind of on top of everything I'm doing here, I guess. I don't know where to move this here. Okay, it's going to be 1 over the object distance of, that is 22.8 centimeters, plus that one is going to be 1 over a negative 64.8, right? 64.8 centimeters, parentheses, and then invert that to get the focal length, and I come up with focal length of 35.2 centimeters, and that means the person needs about 3 diopters, because this is the way that diopters are determined. Yeah, 2.8, maybe they're going to give her a prescription of 2.75 for the diopters. And of course, for the second part, it would be subtract 3.3 centimeters. The glasses, I guess, are sitting further out, so it would be a 21.7. And this one here is going to be a 63.7, and do the whole thing again. Comes out to 32.9 centimeters. And so these are the two answers, 35.2 and 32.9 centimeters. And again, that one is going to be pretty much 3 diopters. So this one is going to be in centimeters. Comes out with a positive focal length because it's a convex lens for reading glasses. And then, yeah, do it again for 3.3 centimeters here and here, and come up with a slightly different focal length depending on where the eyeglasses are sitting on somebody's nose.